So hello everyone. So my name is Raul Fraile, and I am really excited to be here today talking about data compression and GZIP. It is my first JavaScript conference, and it is really blowing my mind. So before getting into the topic, let me introduce myself. I come from Spain, where I work as a freelance developer. And I am also studying a master's degree in computer technologies, focused on data compression, cryptography, and steganography. So let's get started with data compression. Okay, first of all, I am not an expert of data compression. I am learning about it, and I would like to share with you what I know already. So for me, data compression is an amazing topic. And when I say amazing, it is really amazing, okay, I promise. It can be seen like magic, okay? Data compression algorithms take some data and are able to reduce its size without losing information. In some cases, like in lossy compression, it may be interesting to lose some information, which means that once decompressed, the result will not be identical. For example, in images, sounds, movies, they are more suitable to use lossy compression. While on the other hand, text is usually compressed using a lossless method. For example, in HTML files, JavaScript files, CSS. Okay, but it's not magic at all. We have, for example, tools to determine how far we can go compressing data without losing information, or quantify how much information there is in a given message. And this is thanks to the information theory, which was developed by Claude Shannon in 1948 in his famous paper, A Mathematical Theory of Communication. Okay, so how can we determine how much information is contained in a message? Okay, that measure is the entropy. The entropy, okay, you can forget the formula for now. The entropy is the average number, the average amount of information contained in each message. In binary, for example, we can consider entropy as the number of bits to represent a message without losing information. The concept of entropy is quite abstract, and it is not always easy to understand. But and how a message can contain more information than other, okay? It doesn't make any sense. Imagine, for example, these two places, Berlin and the desert of Arizona. If we say it's raining in Berlin, it is containing less information than if we say it is raining in the desert of Arizona, just because it is less common. Okay? In Berlin, they have 225 days, rainy days per year, okay, 62%, while in the desert of Arizona, only 17 days, which is 6%. So information theory and entropy is closely related to probabilities, as you can see in the formula. And while this is mostly theoretical, our brains are already designed to compress data. Okay? We do it all the time. For example, we use emoticons to express complex information like feelings. Okay, with just a couple of characters, we can communicate that we are happy, we are sad, we are mocking you. We also use acronyms for common sentences. We no longer say laugh out loud. We just say LOL or ASAP for as soon as possible, saving time while speaking and saving space when storing it. Even in real life, we can share so much information by our facial expressions. Okay? The kid's face is telling us that he feels safe, he's happy, and is having a great time. Of these two examples, we could consider emoticons and facial expressions as a form of lossy information, of lossy compression, sorry. Information is being missed here. On the other hand, acronyms, if they are unique and well-defined, okay, we can decode it uniquely, would be a form of lossless compression. But even before information theory was developed, data compression was already a key factor to design codes to communicate. Take the Morse code, for example. to save time and bandwidth, Morse code assigns shorter codes to more frequent characters. For example, in the English language, the most used character is the letter E. So in Morse code, it is the shorter code. It is just a dot. So what about data compression in websites? Okay, this is the normal flow. Okay, the browser sends an HTTP GET request to the server to get the file, for example, index.html, letting the server know with the accept encoding header that accepts the zipped content. The server then reads the file, compresses on the fly, usually, and sends it to the browser. Okay? Unless we configure the server to serve pre-zipped content, it does it on the fly. Finally, the browser decompresses the file also on the fly again, and gets the original content. As we will see later, having to compress and decompress file on the fly requires to have a compression algorithm which is fast to compress and fast to decompress in both directions. So after this short introduction to data compression, let's see how GZIP works internally. GZIP is a file format. It is actually a file format which is based on an algorithm, on a compression algorithm called Deflate. The actual compression takes place in the Deflate algorithm. Deflate was designed by this man, Phil Katz, for the PK-zip archiving tool, and it is used, for example, in HTTP and also PNG images, PDF files. Okay. Unfortunately, the history of Phil Katz is a sad one. He was a genius, but he died when he was only 37 due to complications related to chronic alcoholism. So Deflate is a combination of two algorithms, LZ77 and Huffman coding. Let's see how they work. LZ77 is a lossless data compression. Remember, we get the original data once decompressed, which achieves compression by replacing repeated occurrences of data with references. Okay? So in this example, we see how the algorithm tries to find repeated occurrences and, for example, finds that space, file, space, is space appears twice. So replaces the second occurrence with a reference. The first number is the distance, okay, the jump, the number of positions to need to go back to go to the other string. And the second number is the length of the match. So the decoder can uniquely decode that information. To find matches, the algorithm keeps track of recently read data up to 32 kilobytes. This structure is called the sliding window. Okay? We refer sometimes to LZ77 as a sliding window algorithm. So once compressed, we have three types of data in the compressed stream. We have literals, which would be the characters that have not been replaced by references. We have lengths, the length of the match, and distances, the jump. Okay, and in the second step, the algorithm tries to use fewer bits for each of the symbols. Okay? So one approach would be to use only the necessary bits to represent all the symbols. For example, here we have the string hello world. If we use ASCII, ASCII uses 8 bits per character. We would need 88 bits to represent that information, that message. As we are only using the characters that appear in the table, they can be represented only with 3 bits. So we can make a transformation and use only 3 bits to represent the message. So we would need only 33 bits to represent that information. But we can do it better. Instead of fixed length codes, we can use variable length codes. So if we calculate the frequency, okay, the number of appearances of the characters, we can try to assign shorter codes to more frequent symbols, like the Morse code does. So in this example, L is used 3 times. The letter O is used twice, and the others only once. So we could do this and only use 19 bits instead of 33 to represent the message. Okay, but there is a problem. The compressed stream is ambiguous. These 4 bits could be, for example, HE, which is correct, A, which is 00, and E, which is 01. But it could be also LHO, L as 0, H 00, and O 1. Also DO, and many others. So we will need to add an extra mechanism to separate that code, losing compression ratio. And here is when Huffman coding comes. Huffman coding generates variable length codes, also assigning shorter codes to more frequent characters, but they have the prefix property. The prefix property says that any of the codes is a prefix of another. So the output can be uniquely decodable. It is not ambiguous. So using Huffman coding, the message can be represented with only 32 bits, 1 bit less than using fixed code. And for larger messages, gains could be even better. So Huffman code is used using the compressed output we got from LZ77 and creates 2 tables, one for literals and lengths, and the second for distances. So if we go out now to the GZIP file, okay, not the Deflate algorithm, the GZIP format file, it compresses an input data in blocks. Okay? Each block is compressed separately. And there are 3 modes of compression. In mode 1, there is no compression at all. It is usually useful for data that is already compressed or data that is totally random, that cannot be compressed. Mode 2 uses some already generated Huffman codes, using some statistical analysis which fits good enough for most data. And the mode 3 generate these code tables taking into account the data of the block. The mode 1 is the fastest, and the mode 3 is the slowest, but usually gets better compression ratios. As a curiosity, if you are familiar with this image, you probably have used in the past some software to split big files into several chunks the size of floppy disks. That software used to use the no compression mode to make these chunks. Okay, so we just saw how GZIP works. And as you may have noticed, there are different ways to generate a GZIP compliant file. Just splitting the file into several blocks with no compression, the no compression mode, we get a GZIP compliant file. It is really fast, but there are no compression at all. And there are a lot of software able to create GZIP files, okay? And each of them use their own optimizations. So the result will be different. Also, there are compression modes. For example, the high compression mode spends more time in LZ77 trying to find longer matches. Okay? In general, 7-zip gets better compression ratios than GNU GZIP. And for example, zopfli follows a different approach. Zopfli is a product from Google. And what it does is spend much more time, and when I say much more time, it's much more time, okay, around 100 times lower, to get better compression ratios, okay, around 5%. This is really useful if we want to compress, for example, our JavaScript files, our CSS files, before deploying, okay, in the deployment process, and then serve those GZIP files instead of compressing in the fly. As a general rule, using more time, you get better compression ratios. So you need to find a trade-off between doing it offline and uploading the compressed files, or doing it on the fly. So why GZIP? Why do we use GZIP? It is the best compression method. Okay, the answer is no. There are many compression algorithms with better compression ratios than GZIP. So why are we still using GZIP? As most of the times in computer science, the answer is a trade-off. GZIP provides a good enough compression ratio between 2.5 and 3 for text, and it is fast. It is fast to compress data, and it is fast to decompress it. As we usually configure our web servers to compress responses on the fly, this is something to take into account. In addition, even in the worst case, for example, if the data is already compressed, expands the data just a little bit, okay, by only 5 bytes per 32 kilobyte block. As the web server will try to compress everything, it is important to be sure that damages will be relatively low. Also, the memory needed by the encoder and by the decoder is independent of the size of the data. And finally, there are free implementations that avoid patents. It is also difficult to add newer compression methods to be widely used. For example, the Chromium team tried a few years ago to add support to bzip2, which is based on the Burroughs-Wheeler transform and provides better compression ratios than GZIP, and it is also fast. The problem was that even though the HTTP headers were correct and the contents were compressed with bzip2, some all intermediate proxies did not understand it, and instead of letting the data as it was, they changed the headers, so corrupting the data. So basically, in the short term, at least, we are stuck in GZIP. What can we do to try to get better compression ratios? So we can preprocess the data to try to optimize matches. Okay, take a look at this image. This image was generated by a tool called GZIP and shows what parts of a compressed HTML file have been compressed better. Those are in blue. And what parts have been expanded. Okay, so we can see that strings of characters in uppercase, or sometimes the first character of capitalized words, expand. This is the expected behavior, as they are less common and it's more difficult to find a match to replace by a reference. But could we preprocess this data to try to optimize the compression? And the answer is yes, sometimes. The goal would be to have a function T, in orange, able to transform the data in a way that once zipped, it is smaller than the original data zipped, without losing information. And this depends highly on the type of data we are using. For example, in JSON files, there is a technique called transposing JSON. As you know, a JSON object is made of key value pairs, where the key portion is repeated for each instance. The basic idea is to group together all the values for each property. So in the example, the name property will contain all the names, and the country property will contain all the countries. Obviously, we would need to change our client-side JavaScript to be able to read this. But doing this, we have two main benefits. The first one is that we reduce redundancy. We are making the file smaller at the expense of spending more time or CPU cycles in the client to interpret that information. But we are also grouping similar data together. If you remember when we talked about LZ77, it has a sliding window of 30 kilobytes. For large files, we make sure that similar data, okay, in this case names or countries, will be close. So it is more likely to find matches between similar data. It is important to note that not always we will better compression rate with this technique, so we must be careful. For XML and HTML files, I have been working on an automatic process able to order attributes in a way that maximizes LZ77 matches. Here, executing LZ77, only LZ77, not the Deflate completely. Over the first sample, we get an improvement in the file size of 17%. As attributes get more ordered, we see that the percentage is bigger. So in general, if we follow a pattern to order our attributes, we'll get slightly better results. The process is not as simple as also takes into account the value of the attributes. But just having a kind of standard to organize your attributes, you will get better results. If you are interested in this, there's a link at the bottom with a small paper on it. So finally, if you have interested on data compression and GZIP, okay, some recommended material. Compressor Head is a series of videos of data compression. Okay? They are done by Cole McCandless, which works at Google, and makes it really easy to understand and funny. Okay, I also want to thank him for reviewing this presentation. This is my favorite book on the topic. It is Data Compression, the Complete Reference. I am not sure if it's the best idea for a beginner to start with this, but if you are curious to know how a given algorithm, okay, one concrete algorithm, probably the answer is here. Okay? The book is quite expensive, so if you are not going to read it, don't buy it. And if you like reading papers, I recommend to read this one from JSConf EU and Abraham Limpel, which they talk about LZ77. LZ comes from Lempel-Ziv, okay, their subnames. And finally, the paper written by David Huffman on the construction of minimum redundancy codes, okay, the Huffman coding. It is a very short paper, around 12 pages, but the impact on data compression and other fields have been huge. And that's all. Thank you, and hope you enjoyed.